Flexible members such as cables, chains, and wire ropes represent an important class of structural elements in a wide variety of applications. These include electrical transmission lines, cable-stayed suspension bridges, tower guy wires, and some roof suspension systems. In this section, we will discuss 3 common types of cable loads. The first load type involves single or multiple concentrated loads applied randomly along the cable's length. As shown, such loads pull the cable into a series of straight-line segments, so the cable's shape resembles some portion of a polygon. The second type of load consists of equal concentrated loads applied at equal horizontal distances across the cable span. These loads produce a cable shape whose smooth curve is defined mathematically as a parabola. The analysis of both types of concentrated loads generally assume the weight of the cable is negligible compared to the applied loads. The third type may be described as equal loads applied at equal distances along the cable itself. Cables having uniform weight per length and external loads such as snow and ice may also be considered as uniform along the cable. These types of loads pull the cable into a smooth curve called a catenary curve. The first load type we will discuss is the concentrated loads at random locations. For loads similar to those shown, our analysis makes the following assumptions. 1. All loads are in the plane of the cable, i.e., the system is coplanar. 2. The cable is flexible and produces no resistance to bending. 3. Weight of the cable is negligible compared to the applied loads. And 4. From assumptions 2 and 3, the section of cable between any 2 adjacent loads behaves like a two-force member. Because reactions at each end of a cable generally have both vertical and horizontal components, a free body diagram of the entire cable has 4 unknowns, and the system is statically indeterminate. Let's look at the first example. Cable ABCD supports 2 concentrated loads and spans a distance of 28 feet, as shown in the figure. The distance along the cable from support A to the 150-pound load is 10 feet. For this cable, determine the following: the tensions in portions AB, BC, and CD of the cable, the maximum cable sag H, and the total length of the cable. The first step, as always, is to draw your free body diagram and apply your equilibrium equations to find whatever you can from the forces. We have 4 unknown forces here, so this problem is going to be an indeterminate problem. Let's find the expressions for the values that we can. By applying the equilibrium equation, the summation of forces in the x direction is equal to 0, AX will be equal to DX. By applying the summation of y forces is equal to 0, and the summation of the moment about A is equal to 0, we will be able to find the value for dy as 192.9 pounds and AY as 207.1 pounds, but we will not be able to find the values for AX and DX. Using the same technique as in our analysis of structures and machines, we then make a free body diagram of portion AB of the cable, as shown in figure 6.36. We apply the equilibrium equation to that portion. We know that there is tension in member BC, and if we take a moment around B, we will be able to find the value for AX as 155.3 pounds. Applying equilibrium equations, summation of x forces equal to 0 and summation of y forces equal to 0, we simplify the horizontal and vertical force equations to find TBC times sine theta equals 57.1, and TBC times cosine theta equals 155.3. If we divide the two equations, TBC times sine theta by TBC cosine theta, we find the tangent theta equals 0.36768. Then theta equals 20.19 degrees, and TBC equals 165.4 pounds. From the free body diagram of point A, shown in figure 6.37, using the Pythagorean theorem, RA equals TAB equals the square root of AX squared plus AY squared equals a resultant value of TAB as 258.9 pounds. Similarly, figure 6.35 tells us that AX equals DX equals 155.3 pounds. So the free body diagram of point D, shown in figure 6.38, yields TCD equals 247.6 pounds. If you want to find values for the angles, our free body diagrams also yield geometric information that may be useful in parts B and C of this problem. From figure 6.37, tangent alpha equals AY divided by AX equals 207.1 divided by 155.3 equals 1.3335 with an alpha angle of 53.13 degrees. Likewise, from figure 6.38, tangent beta equals dy divided by dx equals 192.9 divided by 155.3 equals 1.2421 with beta angle of 51.16 degrees. Notice that although the vertical force components are different for each portion of the cable, the horizontal force components are the same at all points along the cable. In other words, AX equals TAB times cosine alpha equals TBC times cosine theta equals TCD times cosine beta equals dx. Then we will proceed to the second requirement, which is to find the total sag of the cable. The geometry of cable segment CD is shown in figure 6.40, where angle beta is 51.16 degrees. Trigonometry yields CD times cosine B equals 10, CD equals 15.95 feet, CD sine beta equals H, or the sag, equals 12.42 feet. Similarly, the geometry of cable segment BC is shown in figure 6.41, where angle theta is 20.19 degrees. Then, BC times cosine theta equals 12, BC equals 12.79 feet. And total cable length LC becomes LC equals AB plus BC plus CD equals 10 feet plus 12.79 feet plus 15.95 feet. LC, or the length of the cable, equals 38.74 feet. The second cable load type is the equal loads at equal horizontal distances. The most common example for this type of loading is the basic suspension bridge. Weights of bridge deck, roadway, and vehicular traffic are transmitted to the main cables by equally spaced vertical cables called suspenders of varying lengths. Cable weights are generally considered negligible compared to those of the deck and roadway. It is common practice to describe the weights of the deck and roadway as a uniform load per unit length, for example, in pound-foot or Newton meters, rather than to designate the concentrated load applied to the main cables by each vertical suspender cable. Uniform load is determined by dividing the total weight of deck and roadway by the span of the bridge. To help analyze the parabolic curve formed by the main cables, we may locate the origin of a rectangular coordinate system at the lowest point, called the vertex, on each cable as shown. For analysis purposes, The same assumptions used in the case of concentrated loads at random locations will also be applied here. From the free body diagram shown, the horizontal and vertical equilibrium equations become T cosine theta equals T and O, T sine theta equals W. The force triangle yields the relationship of big W equals small w times x. By applying the third equation of equilibrium by taking moment about the general point B located at the right end of the cable section shown, we see minimum cable tension exists at the vertex, while maximum tension occurs at a support. The generic equation will look like this. T equals square root of TO squared plus small w times x squared. In the case of symmetrical cables or supports at same elevation, we may substitute the coordinates of a support, x equals L divided by 2, y equals h, to obtain this relationship for T minimum. We will also be able to find an expression for the maximum, which is at the supports. Finding cable lengths for parabolic shapes can be a lengthy process and generally involves calculus. Most analyses use standard formulas to approximate values for length of cable and amount of sag. These formulas are known as infinite series and are subject to certain conditions. For a symmetrical cable having span L and sag H, cable length LC may be approximated using the first three terms of the series. Quantity, H over L, is known as the sag ratio and generally has a value between 0.05 and 0.20. This equation is only valid for a small sag ratio, H over L, where the slope of the cable is 45 degrees or less. Let's look at another example. The symmetrical cable of figure 6.45 has a span of L equals 30 meters, has a sag of H equals 2 meters, and carries a uniform external load of W equals 3,500 Newton meters. We are asked to find A. Find the T minimum and T maximum for this cable, B. Determine the required cable length LC, C. Repeat A and B if H equals 4 meters. Because the cable system is symmetrical, we have an expression for T0 equals T minimum equals WL squared over 8H. T max equals WL over 2 times the square root of 1 plus L over 4H squared. Plugging in the values for L, H, and W, we find the values for T minimum 196.9 kilonewtons, and T maximum, 203.8 kilonewtons. For part B, we want to use the approximation equation to find value for the length of the cable, but first, we must check the restriction for a maximum cable slope of 45 degrees or less. We have the equation tangent theta equals Wx, divided by T0 equals 0.2666. Theta equals 14.9 degrees, which is less than 45 degrees. This equation is good to use. Then we plug in our equation for the length of the cable. LC equals 30 meters times the quantity of 1 plus 8/3 times the square of 0.066667 minus 32 over 5 times 0.066667 to the 4th power. We find that the length of the cable is about 30.4 meters. We can repeat the same steps to find values if the sag was 4 meters instead of 2. Those values would be T minimum equals 98.4 kilonewtons, T maximum equals 11.6 kilonewtons, and the length of the cable equals 31.4 meters.